In this concept, we're going to talk about graphing polynomial functions. To graph a polynomial function, we construct a table of values, right? So we have the function f of x, and then we have some values x which lead to the values of the function. And then we plot the values on the coordinate plane, then connect the points to make a curve, and just describe the end behavior of a function. The end behavior of a function is the behavior of the graph as x approaches positive infinity or negative infinity. Then another important aspect of polynomial functions is whether they are even or odd, okay, even degree or odd degree. Now, even degree polynomial functions, if they have a graph that intersects the x-axis in two places, the function has two real zeros. For example, a parabola like this, right? So two real zeros, right? If the graph of an even degree polynomial function does not intersect the x-axis, the function has imaginary zeros. So if the parabola is like up here, right, if it doesn't intersect the x-axis, the zeros are imaginary. If the graph of an even polynomial function is tangent to the x-axis, the function has two identical zeros. So if it's a parabola that's like this, right, and it's tangent, or like this, right, then it's this value of x twice. That is the zero. Or that's the same zero, duplicate zeros. The graph of an odd degree polynomial function always has at least one real zero. In other words, the graph intersects the x-axis at least once. Okay, so an odd function has to intersect the x-axis at least once. Let's look at some examples. Graph the function f of x equals minus x cubed minus 4x squared plus 5. So we start by creating a table of values like we said. So typically you want the origin, 0, right, for x, and a few digits on either side. So you can go up to, minus 2 and 2, or you can go up to minus 3 and 3, or minus 4 and 4, etc. Here we like to make it a little bit, extensive, so you can see the behavior of the function. So we went from minus 4 to 4. So then you take all these values of x and then you plug into this function, right? And then you get all these values of f of x. So at minus 4 for x, the function value is 5, etc. Minus 3 for x, the function is minus 4, etc., etc. And then we plot the table of values on the coordinate plane. So this is an odd degree polynomial function with a negative leading coefficient. So this means that the graph intersects the x-axis at 3 points, right? So it's a cube. So the function has 3 real solutions. As x approaches plus infinity, the function approaches negative infinity, right here. Right? So as x goes to plus infinity, the function keeps going to negative infinity on y. And as x approaches negative infinity, the function approaches positive infinity on y. Okay? Locating the zeros of a polynomial function. The graph of a polynomial function intersects the x-axis somewhere between pairs of x values at which the corresponding f of x values change signs. So usually when there's a sign change, the zeros are somewhere in between, right? So you can see here that at negative 2 for x, the function value is 9. At negative 1, the function value is negative 1. Right? So here, obviously there's a 0, right? From 9 to negative 1, so there's a change in sign, so somewhere between here, it crossed the for from 1 to negative 3. Again, somewhere between here, there's a 0, right? There was a cross, it crossed the x-axis. And here also, from minus 7 to, whatever the next value is, right? 19, it's way up here. Again, somewhere in between here, there was a cross and sign. Okay. Determining maximum and minimum points. The relative maximum is located on the top point since no other nearby points have a greater y-coordinate. The relative minimum is at the bottom point since it has lesser y-coordinates. These points are called turning points on the graph, and the graph of a polynomial function of degree n has at most n minus 1 turning points. So kind of like here, right? You see they are turning points. This would be like a local minimum. This is the absolute minimum of the function. This would be like a local maximum, right? Okay, let's look at another example. Graph this function. So f of x equals x cubed minus 3x squared plus 2. Estimate the x-coordinate at which the relative maxima and relative minima occur. First, we make a table of values like we have been doing. So here we expect the 0 to occur around, the 0 for y to occur around x equals 1, so that's why we started from negative 2 to 4. Again, you could have started from negative 4 to 4, negative 3 to 3. Again, this is a, trial and error. So at minus 2 for x, the function value is minus 18, so it's all the way down. At minus 1, the function value is negative 2, so it's approaching here. At 0, the function value is 2, so we know that the first x here is between, so minus 1, right? Minus 1 is somewhere here, right? Where you get minus 2 for the function. So here is the, here's 1, 0. And then at 1, here's another 0, right? At 1 for x, y is 0. And then 2 and negative 2, and then 3 and 2, and then 4 and 18. And that's another 0. Okay, so the values of f of x change signs at x equals negative 1 and x equals 0. X equals 1 and x equals 2. And x equals 3 and x equals 2 and x equals 3. So all these are the zeros. So the value of f of x at x equals 0 is greater than the nearby points, and we can see that from the graph. So this is a relative maximum, right? So x equals 0 is a relative maximum. The value of f of x at x equals 2 here, which is this point, is less than nearby points, so it's a relative minimum. Okay. And here's a quick exercise. Please pause the video, work on this, and come back for the solutions. Okay, we need to graph this function, f of x equals 2x cubed minus 3x plus 2. So first, we can create our trusty little table of points. And we can pretty much start from maybe minus 2, should be fine. But again, it's trial and error. If we need more values, we can just add them. So when x is minus 2, f of x is minus 8. And again, you can use the calculator to confirm these. When x is minus 1, f of x is equal to 3. When x is 0, f of x is equal to 2. When x is 1, f of x is equal to 1. When x is 2, f of x is equal to 12. And then we can create a coordinate plane, and then we have minus 1, minus 2, minus 1, minus 2, and then this is really 5, 10, minus 5, minus 10, right? So minus 5, minus 10, 5, 10, 1, 2, minus 1, minus 2. Okay, so minus 2, we have minus 8, which is somewhere here, right? It's a little bit off, somewhere here. Minus 1 is at 3, which is here. At 0, we're at 2. Whoops, what happened? At 0, we're at 2, which is somewhere here. And at 1, we have 1, which is here. And then at 2, we have 12, which is all the way up here. So we have something that looks like this. And it would only make sense that it would go through the x-axis like this. Okay. And this is it. That's it for this video. See you in the next video.